What's the crack, YouTube? Today I'm making a video about a little project I have coming up. It's basically connecting a 19 kilowatt blower. For anyone that doesn't know what a blower is, it's a large three-phase motor. It doesn't have to be three-phase, but it's a large motor and a fan, centrifugal fan, and it blows a lot of air. So it's going to be installed in an industrial premises, and basically it's too large to start with direct online starting because it's 19 kilowatt. It's a significant amount of power, about 35 amps or so kind of running current, so it's going to want a soft starter to start the motor. So I will have a video coming up which will probably demonstrate the installation of the equipment and so on, but the purpose of this video is to kind of show people how I go about creating a schematic for what I have in my head and how I plan on wiring it. And it's also nice to be able to do because you can leave the schematic with the customer and then they have a wiring diagram for future use, you know. It's very similar to stuff that you would do in your apprenticeship if there's any apprentices or newly qualified people that are watching this video. And yeah, you'll see some similarities with how I do my work because it is pretty industry standard anyway, the stuff that you'd be doing in college. But there's ways that you can advance your skills with kind of putting this to practice a bit more. Sorry, my light's flashing up and down a little bit. Don't know why. Power supply. But yeah, that's the story. So I'm not going to spend too long here. I'm going to get straight over to the drawing. It's going to be a long video, by the way, so you can skip through it if there's different parts that you want to watch. So yeah. So I've printed off a few data sheets here, and these are basically the main components that are going to be used in the project. So what we have is we have a thermal overload relay, and this variant of overload relay, it doesn't actually have any kind of normally open or normally closed auxiliary terminals. So that's what this fella here is. It's basically an add-in module. So you remove this piece of plastic here, and this fella will just snap in, and basically, you know, it'll be in the state of normally opened here, normally closed, and then if this trips, they're going to go to the opposite state. So that's the little auxiliary module that goes into the thermal overload relay, and I also have the kind of internal schematic for the overload relay. So there's your, you know, your thermal, your bimetallic sections, and you know, the trip part of the relay. Another component we have, I don't have the picture, but I'm sure everyone's familiar. It's just a 3-pole contactor, and this one's rated to 50 amps. It's rated for 22 kilowatt. I'm not exactly sure what the AC rating is on it, but it's 4 motors anyway. And the expensive part of it all, the most expensive part, is this fella here, which is a Siemens soft starter for the 19 kilowatt motor. So it's a 3-phase induction motor, as I said. And basically what this fella does is, it's just a little internal schematic for this. Basically, you supply this with the control voltage, and in this case it's 230 volts, so one of the phases and neutral. And basically you supply A1 and A2 with your 230 volts, and then, you know, on your input side of the soft start, you're going to have your 3 phases of line voltage. And you also have an auxiliary relay here, and that's for when the soft starter is active, you know, and the motor is running. The principle of operation with a soft starter is you have 2 triacs, which are and they also have bypass relays for when it gets up to full speed. But basically it's using, you know, pulse width modulation to kind of slowly ramp up the current into the motor on these 2 phases. As you can see, the center phase, that doesn't have a triac, so that's directly connected to the motor. But you have an adjuster here where you can adjust the kind of ramp up speed, which is, you know, it's only going to be less than a second, you know, so it's fast how quick it operates, but it's quite important so that you're not putting a huge amount of strain on the motor. When I say it's less than a second, it might be, you know, 1 or 2 seconds. I'm not fully sure, I haven't looked into it, but that'll be part of the commissioning process. So yeah, so those are the main components that we have, and like I said, with some other components. So obviously for any bit of electronic equipment you need your main overcurrent protection, which in our case will be a 3-phase MCB. There'll also be a control MCB, a single phase MCB, and that'll be to supply kind of the controls for contactors and switches and so on. In this case, just using 230 volt control circuit. That's what all the components are, and I just wanted to keep the costs down for the customer, and you know, not to have additional power supplies put into the picture. So yeah, basically what I have as well is I have some graph paper, and that'll be the basis for, you know, drawing your electrical schematic for what you intend to build. And this is the part, you know, that you touch on a little bit in the apprenticeship. I don't know if there's many apprentices watching or people who've recently qualified. You'll be familiar with the terminology that's used. But yeah, so the components we're going to be using are there'll be an emergency stop button and a start button. There'll be a run lamp and a trip lamp, run indicator, trip indicator. There'll be a contactor, and the reason that a contactor is important in this case is if we go back to the schematic of the soft starter, wherever I've put it, where have we got it? Here. So as I said, there's nothing that's actually, you know, isolating the three lines that are coming in here. You've nothing actually isolating, say, the middle section of this device, so it'll have permanent 400 volts to neutral output on this in the center terminal, you know. So that's why you're going to have a contactor upstream of the soft starter, and that's important just with regards to safety, because what you don't want to do is, if you only had a soft starter and your thermal overload relay, say for example, you know, something happens with the motor and a different electrician for whatever reason is called in to make a repair on the motor, say you're not around, you know, someone might think, oh, I've hit the stop button, surely the motor's dead. And you know, wise electricians will open up the motor and you'll check with your multimeter, but you can't take chances when you're talking about three phase, especially, never mind single phase. They're all as dangerous as each other. So yeah, there's a contactor upstream. What else is there? As we said, we have to overload relays and so on. So I have already drawn it out on a separate piece of paper, but I just thought it'd be neater for the customer if I put it onto some graph paper, and then I can scan this and send it on email so that they'll always have a copy, and then I can print it and give a physical copy as well. But yeah, it's very similar to what you'd see in college, you know. So just going to start off with a heading here. So this will be the control circuit. And yeah, so basically what we have up on the top of our control circuit is, as we said before, there is two 30 volt for the control circuit. Two 30 volt. Okay. Now what I can do to make it neat is on the bottom we can put another line across, and that could be for our neutral. 0 volts neutral. So it's 0 volts because it's referenced to ground. 230 volts. It could be any line conductor, but for instance in this case we'll say L1. And to start the control circuit, we do what we would always do, and we'll put our control MCB in the top. So we're going to bring a line down here. I'm going to draw your fuse symbol, and then I'm going to designate this as F1. It's the first fuse that I'm going to be using, and this will be most likely a B10. Doesn't really need to be a C because it's only contactors and so on. So then after F1, okay, some people put the dots in, some don't. I'm just going to do it for demonstration purposes. But basically what we're going to have after F1 is our auxiliary contact, so for the trip relay. You want any fault that can occur, you want the fault to be able to isolate the whole circuit, the contactors, all the controls. So your thermal overload will be the first thing in the series line. So what we have here is we have a normally closed connection, so when it's in normal state, non-tripped, this will be closed. So 21 and 22. What I'm going to do here is I'm just going to continue the line down, and this will be trial and error as well. You might start a drawing and you'll make a muck of it and you'll have to go again. So yeah, and parts of this video I'm going to speed up as well because I'm conscious that it's going to be slow enough process. But yeah, after your overload relay, we'll have a section here, and then that'll be going on to the next step. So we're going to draw normally closed. get my head in the way as well during this video. We have 21 and 22, and this will be different for different relays. You know, if you have the add-on module for a Schneider contactor, they'll be 95, 96, 97, 98, but basically you just want to make sure you have your normally closed at the start of your control circuit. You can number it as well if you want to be neat. You don't have to. It's easier to kind of, especially if you're wiring it, it'll be easier to make sense, or for anyone else who has to go at the circuit that you've built. But I'm going to designate this one as F3. The reason being is that I'm going to keep F2 separate for the power MCB, which is what's going to disconnect the power circuit to the motor. So F3, that's going to be our overload relay, and then the next step is going to be the emergency stop. Then we're going to have the standard stop button, which is the operational stop. That's what you'll use to turn off the machine rather than hitting the E-stop. And they're both going to be normally closed, as they usually are with stop buttons. And this is, you can always, you could go to different extremes. You could be adding in safety relays and everything into this if you were, you know, if it was required, but in this case it's not going to be required. So here we have the E-stop, and the symbol for an E-stop is like that, with the little section in here, and that indicates that once you hit the stop it won't spring return. So like that, and we're going to have 1 and 2 for normally closed, and we're going to call this S1, switch 1. Likewise, we're going to have 1 and 2, have our dots coming across, and this one here is a standard stop button, S2. Then after the stop button, we're going to have the start button. Okay, and that's what's going to initiate the control circuit, energize it. So put in our other little dots, and this is going to be 3 and 4 for the case of a normally open contact, S3. We'll do a legend after as well, and we'll be able to label each of these. But this will be our start button. So I haven't really gotten a drawing as to what it's going to look like, but basically, you know, if we had the enclosure, which is already on site, you know, and you have your 4 screws for taking the lid off the enclosure. You might have a keyed door type enclosure, but basically there will be an E-stop here, should have your little emergency tag around it, and then you might have your green start, and you'll have your red stop buttons. Then, you know, you can put them up here, you can put them over here, but you'll also have your run light, and these can be labelled as well, and you have trip. And what I've ordered is a green run light and an orange trip light, so that if something is tripped, they know it's tripped and they can open up this enclosure, reset it. Maybe it's been started and stopped a few too many times and it's just heated the bimetallic strips, or maybe there's an issue and it'll trip again, but that's the purpose of it, to give indication. So we have our start button here, and that's going to be normally open, and after the start button it's basically going to go down to the coil of the contactor. This is the main motor contactor, and I'm just going to, you know, I'm not going to spend too long doing this. We get the gist, but I'm going to call this KM1, like you would in college. KM1. Okay, so we have we have our start button, KM1, and then that goes down to neutral. Hope this is all in the shot. Yeah, I think it is. So like that, and what these are going to be, when I say designated, I don't even know if that's the right word. Throw words out at random, so I do. But yeah, as you can see here, for the contactor you have A1 and A2, and when you supply 230 volt across it, in this case the 230 volt coil on the contactor, that's going to pull the 3 main power terminals closed. It's going to close 13 and 14, the normally open auxiliary, and it's going to open 21, 22, which is the normally closed auxiliary. So yeah, what we're going to do is we're going to write in here A1 and A2, and that's for our contactor. So now, as we know then, if we supply power here, okay, so we've 230-volt coming down. If our trip overload relay is okay, if it's non-tripped, power will continue through here. Then if our emergency stop is released and everything is in normal state, power will continue through that. Nobody's holding in the stop button and it's spring return, so that will also be closed. Power continues down and then it stops here. So if the operator wants to start the blower or the motor, they're going to press S3 and that's going to power the coil of the contactor and it's going to pull it in and send the 3 phases out through the contactor. But obviously if we release S3, it's going to release the contactor and you lose power. So what we need in this case is a hold-on contact, which I'm sure people are familiar with that term as well. So for the hold-on contact, what we're going to do is we're going to bring this section out here, and basically what we're going to do is we're going to put in another contact in parallel with the start button. As you know, you put stop buttons in series, but start buttons go in parallel. And if we look at the contactor, we have these 2 auxiliary contacts which follow, you know, the state of the main power contacts, and we have 13 and 14 which is normally open. Okay, so we're going to use those 2 on the face of the contactor. So we're going to label this 13 and 14, little NO for normally open, and we draw our symbol for normally open. So now if we were to press the start button here, we get power supplied to the coil. Okay, contactor pulls in, all these terminals close, 13 and 14 closes, which is basically that shorted out. So now if you release the button, the power it's bypassing the button essentially, and it's continuing to hold the coil on. So that's a hold on contact. So what that entails then is that the circuit is going to stay energized until something changes. So if you have a trip on the overload relay, this opens, and because it's upstream, it'll kill power to the contactor coil. Everything goes back to safe or no power, dead. Likewise, if you hit S1, the emergency stop, that's going to close and lock closed, so that's open. From normally closed, it'll open. You've also killed power. And likewise, if you press the stop button for a moment, the power is going to die here, but because the power has been killed on the contactor, and this, you know, instead of putting NO, I should have put KM1, right? Because that's how we correctly identify it. Okay, KM1. This mimics the state of the contactor. So if you for only a brief period press S2, that's going to open, it'll kill power to the contactor, so this will open up, and then if you let that go, it'll close again, but you've killed the hold on contact, so it won't restart unless you press S3 in. So that's how the hold on contact works. And then after that, what I'm going to do is show how we plan to engage the soft starter, because as we can see on the schematic for the soft starter, this is supplied with power, A1, A2, permanently. But to start the soft starter, so say the motor's not running, how you want to start it is you send 230 volts to the input contact or input terminal on the soft starter here. So the way I'm going to draw this is I'm going to continue our line across. We're going to have something else in parallel here. So basically I'm going to bring this down here. Okay, I'm going to do the same crack. I'm going to draw this little box just like for KM1, and I'm going to call this K1 just for simplicity's sake. I don't know, is there a specific term used for soft starters? Could amend it if there was, but for now it'll do. And basically we have A1 and A2, and I'm also going to put in an additional terminal, and I shouldn't really put K1 so close, but it's okay. I'm going to put another little terminal here, and I'm going to call that 1. So as you can see, this is our kind of relay coil. It's probably not a coil in this case, but we can use that kind of idea. So we have 1, A1 and A2. So A2 continues on to neutral. Now you could, in theory, you could bring A1 from your control MCB, but it wouldn't be ideal because if you have any issues, if you hit the E-stop or if you have a tripped terminal overload, you want that to also kill the soft starter circuit. So I forgot to add in the little diagram for the overload relay, so I'll just add that in now. Looks like a little F, that's how I remember it. But basically, when the contactor pulls in, that's going to, where's my sheet? When the contactor pulls in, that's going to close these 3 terminals here, and that's going to supply power, and that's going to go into the soft starter, right? So it's going to come out of our contactor on the bottom, it'll come into the soft start. So we also want to give the soft start the same, you know, go signal, so that it will start the motor, slowly ramp the current until it bypass relays kick in and it's up to full speed. So essentially what we can do is we can continue on this line here. Let's see, where are we? We can continue this line over from the hold on contact and from the power to the contactor coil, and we can just bring that down and into terminal 1, and it's basically doing the same job. So if we have power here, we have power here, you know, it's like a buzz bar, although it'll be wired with cable. So if the contactor coil gets power, contactor pulls in, and at the same time it's sending the signal to the soft starter. Once the contactor's pulled in, the hold on is going to close, that'll keep this powered, and it'll keep power going into K1, which is our soft starter. And then in the event, you know, you want to stop it, you press S2, it kills power to everything here, and the motor comes to a stop. So what else do we want to add in here? We're nearly done now. So what have we got? K1. Yeah, so we also have this auxiliary contact, and this is on the soft starter, and this is what I'm going to use for the run indicator, because you want an indication that the soft starter is in run condition. Say for example the run indicator is on but the motor is not spinning, you know, there might be an issue with the motor. Now in that case it's most likely going to trip out, but it'll give you an indication as to, you know, the soft starter is still engaged, so there must be something wrong. So basically what I'm going to do is, after the stop buttons, the safety kind of side of the circuit, I'm going to continue this line on again, and that is going to come down into what I'm going to call the K1 auxiliary contact. Okay, so I'm going to come across like so, call this K1, and it's normally open. We have 13 and 14 again, so 1 3 1 4, and we have NO for normally open, and this is going to continue down to our run lamp, or run light as some people would call it, which we'll put here. Do a little circle line through it, and I think they're called X1 and X2, and I'm going to put a label on this L-1. You don't want to call it L1 because it might be mistaken for live 1, which will be phase voltage. You know, up here, L1. Just don't want to mix anything up. So the last thing to include then is the trip light. Saying M a lot at the moment. So in the case of the trip light, trip lamp, we're going to draw a line out from the MCB, and I'll explain why that is in a moment. So we're going to bring that down as well. Go down to the same section that we used for the contacts. Keep it all looking neat. There I go again. Okay, and down to the bottom. Okay, so these are all connected to neutral. So we have another X1 and X2, which are the terminals for the light. L-2 in this case, for the second light. And we have another contact here. I'm going to tell you what I'm going to use. You can probably have a guess. This one's normally open as well. But if we go back to the little module that we're going to use for the terminal overload relay, we have used the normally closed here for the safety end of the circuit. We also have a normally open contact. So if the overload relay trips, this is going to go from open to close. Okay, so we're normally open, NO, and it's 13 and 14. This is our trip lamp. The reason I haven't continued over this line here into the contact is because if we have a trip on the overload relay, this contact here normally closed will open, and this is going to open here. So if we had taken the supply for this from, say, this buzz bar is what I'm going to call it, then if it trips, it's going to kill power to here, so the lamp won't actually function. So that's why we're going to take it from upstream of the contact for the overload. But we're not going to take it obviously from the top, because we need, you know, some form of overload protection for the lamp as well. So that's essentially it. Very simple. And when it comes to wiring it, you know, it will be the same as in the apprenticeship or in college or wherever you are in the world studying. You're going to, you know, coming out of your MCB, it's going to come in on 21 here, and it's going to leave 22, and it'll go into 1 on your emergency stop, out on 2, into 1 on your stop button, and so on. Just follow the diagram that you've drawn out here. You can chop and change this many ways as well. You might have additional stuff. So for example, something that I haven't included is it's an indicator for emergency stop, which we could have a third lamp, and it could be a red lamp, so that if you look at it and it's red, you know someone has activated the emergency stop. How you would do that is, for the modules for the switch, for the push buttons and emergency stops, you can put 3 contacts on the back of a lot of them. So in this case, we've only used one normally closed contact, but you could also have another normally open contact similar to this. So when it changes state, someone has pushed the button, your normally closed will open, but your normally open will close. And in that case, likewise, you're going to branch that from this section here that's coming before all of your safeties. But you could simply add in, you know, it could be a request to the customer, I'd like to make that safer, you know, and inspectors come in and said this is a recommendation, in which case you know, you're going to add simply another contact here, and you're going to add another lamp, and you're going to connect the lamp to neutral, and it's very straightforward. X1, X2, follow the usual, L-3 in this case, and you're going to have your line, and it'll be 13, 14, and what will we call this one? This would be S1, but it'll be your second contact. Could have S1.2 if you wanted. This could be S1.1 if you wanted to improve your diagram. And I forgot to add in, this here is F3, which is another, it's another contact on your overload relay. And you know, you can keep improving your diagram and make it look even better. You know, you can add the symbol in there as well. Just gives a clearer understanding to anyone that goes at your creation and wants to, you know, mess about and fall find on it themselves, maybe even just to take an observation and say, wow, that's great. But that's basically your schematic that you can offer to the customer, and you can say, here, I've built you your equipment, works as intended, but here is, you know, wiring diagram. It's also, you know, another step to make yourself look more professional is you can include the schematics and data sheets. Like, these are only a couple of pages, but there's, you know, full pages for all this equipment, which I order from Radionics or S most of the time. You can get it from Domene Electrical as well. And you don't have to print every single sheet with regards to, you know, this end of it. It might be nice to print the control circuit and the power circuit so that it could be left in the enclosure or left in a file, but you don't necessarily need to include all of these in a physical copy. It might even just be on an email. You could have a folder, it's the extra equipment. But you know, someone else might look at it and go, well, I'm only being paid X amount and that's way over the top, I'm not going to go through all that bother. So that's only one step of the process. You have a second diagram, which is your power circuit, but it's a lot simpler, to be honest. So I'm going to go through drawing that out. I've already done it as well, but basically I'm going to go to a new page, and I'm going to put another line. I'm going to call this power circuit. And this is where your 3 phases connect to the motor through all of the equipment that you've installed here. So, like the last drawing, I'm going to put a line across. It doesn't have to be too big in this instance. And that's going to be L1, comma L2, comma and L3. It's a very funny looking and sign. Okay. And we're going to put in 400 volts, which is our phase-to-phase voltage in Ireland and many parts of the world. So, same kind of idea. Move it over a bit because the ruler is not friendly where it is. I'm going to bring this down to here. Okay. And what we have first and foremost is, if you can remember, I said I was holding F2 free so that we could use that in this diagram. This is F2, and this, in this case, it's going to be a C40 MCB. C40. Now this is actually in a separate enclosure, which is supplying the enclosure that all this equipment is going to be in. And there's also RCD protection, which is just in my opinion wise, considering there's people with their hands operating and there's some water around the area. The blower is going to be used for drying purposes. So we have our C40 3-pole MCB. Okay, and that's the first step. So what I'm going to do is I'm going to put a contact, and I can make these ones bigger because there's a lot less in this diagram. I'm going to draw my line, draw this, connect this up here, and we can go 1, 2, 3, which is our indication for 3 phase. We don't have to draw the 3 separate terminals. That's indicating that we have 3 phase going through here. Now, just for example, with 3 phase, if there was 3 phase in neutral and it was 4-pole equipment, you'd have 1, 2, 3, and you'd have 4. And then you would also have an additional one if you had earth. But in my case, I'm not going to do that because we don't require a neutral. This is a 3-phase induction motor. We only need the neutral for the control circuits, and I have the earth connection directly to the motor, so there's no problems there. So what we have is KM1. I don't know why I drew it over there, but however. And we're going to come down, and then this here is going to be our K1. Okay, so we put in the little box. What I'm just going to do is I'm going to just draw a little kind of thyristor type circuit, just so that we know what it is. So that's what's, you know, controlling the voltage going to the coil windings to slowly ramp up the motor. When I say slowly, in seconds I'm talking about, but it's slower than direct online, which would just be a contactor and a lot simpler. In this case we're calling it K1. Then after K1, prior to the cables entering the motor, we have our final step, which is going to be our F3 is F2 in my last drawing, and then I realised I wanted F2 for the, you know, the power MCB. So this is our F3, and we don't know, yeah, no, that's how you would draw. You can see actually in the schematic for the overload relay, that's what we have. We have the little bimetallic strips, just an indication as to what it is. 1, 2, 3. As I said, I've already indicated that we have 3 going into the different devices. So then that's just going to come out of our overload relay, coming into a nice big circle here, and our symbol for a 3-phase motor. And then simply we have our earth connection to the motor. And that's all there is to the power circuit. There's no need for a neutral because, as I said, it's a balanced 3-phase load. It's an induction motor, doesn't require a neutral. The only thing that does require a neutral is the control circuit, because that is 230 volt and don't connect line to line to any equipment in this diagram, because I've got equipment that has control voltage of 230 volts. That being said, you can get contactors that are 400 volts coil, and your A1 and A2 is supplied with 400. In such a case, you're going to have L1. Well, it probably would be for a control circuit. For an example, if I just go here, you know, if you had a coil of a contactor, you know, you mightn't have a neutral available, and you have your A1 and A2. I've messed them up as well. Okay, but say that's 400 volts AC, doing everything upside down. That means that you could supply L1 and L2 to this contactor and it'll operate fine because it's a 400 volt coil, and that will, you know, in turn pull all your contacts closed. And then when you release your 400 volt, they'll open, but that's not something that's going to be, you know, common that I see anyhow, because you don't want 400 volts running through switches and stuff, especially around water. Ideally nowadays, you know, control circuits are done in 24 volt. You have a power supply and everything, but just with availability of parts and stuff at the moment, they were a lot quicker to order in the 230 volt range, and some stuff wasn't available in 24 volt. So yeah, I suppose the final thing then for me to add in within all of this would be the legend, you bleeding legend, as they say in Dublin. And you could simply do that on the graph paper as well to save some resources. Draw 2 lines here. Am I still recording? Oh yeah, that'd be a shame if it wasn't. A line here, a legend. And we're going to do what we done in the last drawing, which is S1. Just bear in mind I made this drawing myself, 2 drawings from scratch. It's not something outside your means, you know. Once you practice it a couple of times, you get a bit more efficient at doing these drawings and you get better at it with practice, you know. So it's not like I've gone online and copied this from someone. I did create it from scratch. We have our S1, S2, S3. We have K1. We have K1. And these are just, you know, as I said, these are all the different labels that we've used around our drawing. There's F1, F2, F3, we have L1, L-1, L-2, L-3, and try to speed up some of this video because it's going to be pretty long. Dot, 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 dot. We have our E-stop. Yeah, I will speed this up and I'll just not talk. So now that's our legend done, and that's all you have to do. The next step is putting the equipment into the enclosure and wiring it. And you know, depending on the feedback of this video, it might be something that I'll even get into because it's something that I'm going to be doing during the week. And yeah, it might be a good exercise even for myself just to practice the video and skills with regards to, you know, making a diagram like this and then actually displaying what it looks like in practical terms, having been installed. Suppose reflecting on it, if there's, I'm trying to think, is there anything else that I can add, you know. So I've had a little ponder there and there's not too much I can think about adding to the video. So I suppose one thing I could say is that it's not necessary to always use a soft starter with regards to a 3-phase motor. So they say if it's 5 kilowatts or less, okay, less or equal to 5 kilowatts, you can use D.O.L, which is your direct online starting, which is simply a contactor connecting the motor to line. In this case we have 19 kilowatts, which is too high, you know. So what you're going to be looking at is a soft starter, or A or T, or possibly star delta. But in my case I'm not using star delta, and the reason being is that the rating for the 3-phase motor that is situated in the factory is, you have on the motor information plate, you have star/delta, okay, and then you'll have the voltage ratings, which in this case it is Do I have that wrong? Yeah, I have that the wrong way around. So usually it's going to show it in delta slash star. Now in our case we have 230 slash 400 volt, which means that the coil windings for the motor, right, if you can imagine you have your coil winding, it's only rated to 230 volts per winding. Now if you put 400 volts, if you have L1 and L2 here, and you have 400 volts between your two phases, that's divided across two motor windings and they're connected in the center point, which is star. I can make another video on this if people need, but there's plenty of videos on YouTube about it. And you know, if you wanted to use star delta starting, you're going to want a motor which has a voltage rating of 400 690, which means you can connect 400 volts directly in the delta configuration onto the coil windings, and it's rated up to 690 volt in the star configuration, you know, which some industrial applications might have 690 volt and you can connect it in star configuration, but in the case for star delta, you're going to start it in star with 400 volts, which means you're only going to get 230 volts across each winding, which is what is it they say, the current in star is √3 of what the full load current will be in delta, just getting into the complex side of it. But you can use star delta in this case, but if you have a motor rated to this, I would advise against it because you're going to burn out your windings. Might work a couple of times and then it won't after. It's also important to keep this in mind if you were even, you know, direct online connecting the motor. Make sure that it's in the right configuration. You can tell by the motor data plate, it will say delta star, voltage and voltage. And if it's this, you know, you're going to have to be careful. Don't connect 400 volt in delta. So yeah, that's about all I have for this video. Hope you enjoyed it. If it was any benefit, give it a like, it would help out. And yeah, hopefully I'll have more content like this coming up in the future.